Hey everyone, hope everyone had a good Thanksgiving. Welcome back to another week's worth of video lectures. This first video lecture that we're going to do today, we did something like this last week or a few weeks ago. Basically, I'm just going to read you guys the chapter. As you watch this video, questions will pop up because this will be an Edpuzzle, and that will be it for this video. The next video will just be explaining, a mini activity you guys will have to do this week for remote work. But this first video is going to be energy near its atmosphere, how energy from the sun reacts with our atmosphere. And yeah, let's get started. So how does energy from the sun travel to Earth? Nearly all the energy in Earth's atmosphere comes from the sun. This energy travels to Earth as electromagnetic waves. We talked about different types of electromagnetic waves in last week's remote lecture. A form of energy that can move through the vacuum of space. Electromagnetic waves are classified according to wavelength, or the distance between wave peaks. Most of the energy from the sun travels to Earth in the form of visible light and infrared radiation. A smaller amount arrives as ultraviolet radiation. So in the next couple pages, we'll just go in depth a little bit more on each of the types of electromagnetic radiation that reach Earth. All right, so let's talk about visible light. Visible light includes all of the colors that you see in the rainbow: red, orange, yellow, green, blue, and violet. The different colors are the result of different wavelengths. Red and orange light have the longest wavelengths, while blue and violet have the shortest wavelengths, as shown in figure 1 below. We can see that the red light, and red's probably not the greatest color to use on that, we can see that the red visible light has longer wavelengths than purple visible light. So the colors in the rainbow are forms of visible radiation, but there are other forms of non-visible radiation. So the direct transfer of energy by electromagnetic waves is called radiation. One form of electromagnetic energy, infrared radiation, has wavelengths that are longer than wavelengths of red light. Infrared radiation is not visible by humans. It's too low energy for us to see, but it can be felt as heat. The sun also gives off ultraviolet radiations, which is an invisible form of energy with wavelengths that are shorter than wavelengths for violet light. So these are a little bit more powerful than violet light, these have a shorter wavelength. They're a little bit higher energy than the energy of violet light, so we cannot see it. And just like infrared radiation, it cannot be seen, but it can be felt. And ultraviolet radiation is the radiation that causes us sunburns. So that's why we have to, most of us have to lather up when we go to the beach in the summer on sunscreen. So let's take a look at this diagram below. Energy travels to Earth as electromagnetic waves. Identify, label the types of electromagnetic radiation in the diagram below. So we have three types, or three boxes, that we have to identify. The first one, let's look at this section, electromagnetic radiation. I can see right there, those are some longer wavelengths. I can see at the end, they get shorter. In the middle, we have some medium-sized wavelengths, and obviously they're different colors. So let's start in the middle. I think that one is the easiest. Take a second and try to identify which type of radiation that is. All right, and if you said visible light, you are correct. So visible light, obviously, it's all the colors of the rainbow. It's the radiation that we can see. Our eyes are finely tuned to be able to detect that type of radiation. Let's go to the beginning. Let's go all the way to the left. Take a second and try to determine what type of wavelengths you think these are. All right, so if we look at these wavelengths, the wavelengths are slightly longer than visible light. So if you said infrared, you are correct. So once again, infrared we cannot see, but we can, feel as heat. And that leaves, finally, we have the shorter wavelengths. So let's take a second and determine what type of radiation that is. All right, that one should have been easy. You only had one type left. If you said ultraviolet, you are correct. So the wavelengths keep getting shorter and shorter, more high energy. And like I said, those can cause burns, which is why we wear sunscreen in the summer. All right, so on this next page, we're going to talk about what happens to the sun's energy when it reaches us on Earth. So sunlight must pass through the atmosphere before it reaches Earth's surface. The path of the sun's rays is shown in Figure 2. Some of the sunlight is absorbed or reflected by the atmosphere before it can reach the surface. The rest passes through the atmosphere to the surface of the Earth. In the upper atmosphere, different wavelengths of radiation are absorbed by different layers in the atmosphere. For example, some ultraviolet radiation is absorbed by the ozone layer in the stratosphere. In the next assignment, we'll talk a little bit more about the ozone layer in the stratosphere. Infrared radiation penetrates further into the atmosphere before some of it is absorbed by water vapor and carbon dioxide. So you can see in in Figure 2, some of the infrared radiation is absorbed by the mesosphere, but most, gets past the stratosphere and into the troposphere. Visible light penetrates through all the layers of the atmosphere, and ultraviolet, it gets stopped. Most of it gets stopped in the upper atmosphere, and then a little bit more in the mesosphere, and then even most of the rest is stopped in the stratosphere. All right, next we're going to talk about how energy in the form of electromagnetic radiation interacts with the troposphere. So clouds act as mirrors, reflecting sunlight back into space. Dust-sized particles of gases in the atmosphere disperse light in all directions via a process called scattering. When you look at the sky, the light you see has been scattered by gas molecules in the atmosphere. Gas molecules scatter short wavelengths of visible light, blue and violet, more than long wavelengths, red and orange. Scattered light looks bluer than ordinary sunlight. That's why the clear daytime sky looks blue. It may seem like a lot of the sun's energy is absorbed by gases in the atmosphere or reflected by clouds as particles. However, about 50% of the energy that reaches Earth's surface is absorbed by land and water and changed into heat. So on the next page, we're going to look at Figure 3, and we're going to see what happens when incoming sunlight interacts with the Earth's surface. So we need to identify what's happening to the energy in the lower atmosphere and at Earth's surface in this figure. Find out by using the words in the word bank below to complete each sentence. So our words in the word bank are reflected, absorbed, radiated. So let's start at the top. About 25% of the incoming light is blank by clouds, dust, and gases in the atmosphere. So judging what we've learned from previous pages and what we can see going on in this image, take a guess and try to figure out an answer. All right, so for this first question, you needed to decide between reflected, absorbed, and radiated. And if you said about 25% of incoming sunlight is reflected by clouds, dust, and gases in the atmosphere, you are correct. So reflect, so we're going to write for that one. Let me fix my T here. Next, moving down, about 50% is blank by the Earth's surface. This heats the land and water. So decide whether we think it's reflected, absorbed, or radiated. All right, if you said about 50% is absorbed by the Earth's surface, this heats the land and water, you are correct. So about 25% is absorbed by the Earth's surface. All right, next we have about 20% is blank by gases and particles in the atmosphere. So this is this arrow coming down. It's hitting particles and gases in the atmosphere. What's happening? Is it being reflected, absorbed, or radiated? Take a second and decide. All right, so if we look at the arrow, it's coming down, it's hitting something, but nothing's happening. So that leads me to believe, or should lead us to believe, that this energy is being absorbed by gases and particles in the atmosphere. All right, let's do our final two fill in the blanks. So down here, we're going to be talking about these arrows right here. So some absorbed energy is blank back into the atmosphere. Remember, we have reflected, absorbed, or radiated. Which one do we think it is? Take a second, figure that out. All right, so the arrows squiggling back up should have given us a hint. So some absorbed energy is radiated back up into the atmosphere. And finally, about 5% is blank by the surface back into the atmosphere. So we have this big long arrow coming down and then shooting back up. Do we think that's being reflected, absorbed, or radiated? Take a second, figure out an answer. All right, so the arrow coming down and rebounding back up into the atmosphere should have led us to believe that the answer to this one is reflected. So if you answered that for that one, you are correct. All right, so on the previous page, we talked about how some of the energy from the sun is absorbed by the earth and then radiated back out. So let's go a little bit more in depth on that. So what happens to the energy that heats the land and water? Earth's surface radiates some of the energy back into the atmosphere as infrared radiation. Much of this infrared radiation doesn't immediately travel all the way back into space. Instead, it's absorbed by water vapor, carbon dioxide, methane, and other gases in the air. The energy from the absorbed radiation heats the gases in the air. These gases, in turn, hold heat in the Earth's atmosphere in a process called the greenhouse effect. The greenhouse effect shown in Figure 4 is a natural process. It keeps Earth's atmosphere at a temperature that is comfortable for most living things. Remember, the moon, which we talked about, a couple months ago, doesn't have an atmosphere. It doesn't trap heat from the sun in, and that's why in the 6-month day periods we have scalding temperatures above boiling, and then at night during the 6-month night on the moon, we have way below freezing temperatures. So the atmosphere is responsible for this warming effect. Over time, the amount of energy absorbed by the atmosphere and Earth's surface is in balance with the amount of energy radiated into space. In this way, Earth's average temperature remains fairly constant, but scientists have evidence that human activities may be altering the process. So, burning fossil fuels and things like that are contributing to more greenhouse gases being in the atmosphere, and in turn, slightly warming our Earth. All right, so that wraps up this video lecture. After, you guys will have to do some vocab, so you're going to have to define the vocab words using evidence from the book. And I'm also going to ask you guys, a couple quick multiple choice questions that you should easily be able to get. So as always, if you have any questions, let me know. But other than that, have a good rest of your day.